All right, so buckle up because we're going to talk about what is kind of really happening with static hazards, and it can get a little in depth and a little deep, but it's nothing too unobtainable. So first, let's say we've got this three variable function, and just like any other K-map, right? We're just going to say, ooh, there's an implicant and there's an implicant, right? So uh, let's see, what can we do here? Well, the next step is just writing our expression, which in this case, oops, I forgot my labels there, right? 0, 0, 0, 1, 1, 1, 1, 0, and 0, 1. So let's see what we've got. Looks like A is a constant 0. So we've got A naught, C naught. Let's say this is x equals. And they've got or AB. Let's draw what the circuit looks like now. So we're going to have an AND gate, and we're going to have another AND gate. Actually, just to really display this, we've actually got an AND gate where two of the inputs are inverted, right? So I'm going to draw some inverters, and then our AND gate. So this is going to be our A naught, C naught term. So we're going to have A here. We're going to have B here. And C is going to go right there. And then we're going to have a little drop down of A. Have a cat meowing in the background. Just found a sock, which is really adorable. And of course, this is going to go into a big OR gate. And this is X. Alright, so we know that our static hazard is on the edge here. So really, when we potentially can face a static hazard is going from this term to this term, or vice versa. So let's say that we're actually at this term transitioning to this term. So actually, just for color coding, let's look at what our values are here, and then our values when we move here in the transition between them. So let's say that we're at steady state where A is a 1, B is a 1, and C is a 0. This is where we're at. And so let's see. We've got two 1s in this AND gate. That means we've got a 1 here. And that means we've also got a 0 here, right? Because we've got a 1 inverted. And we've got a 1 here. That means the output of this gate is a 0. We've got a 1 ORed with 0, so that means we've got a 1 here. So that's kind of our steady state. We're assuming that everything is steady and everything's been calculated. The other thing is, let's assume that each one of these gates takes 1 unit of time. Doesn't matter what that unit is. It could be zettaseconds, or it could be just seconds. It could be years, whatever. Just 1 unit of time. Now let's look at what happens when we change one value. Specifically, we're changing A from a 1 to a 0. So that means B stays as a 1 and C stays as a 0. So now I did my steady state kind of, I'm pretty sure I still did it in the right order, but let's pay attention to what's actually going to happen first here. And what's going to happen first, right? We can kind of almost think of this in stages. Let's cut this up with some yellow here, right? So we've got a stage here, and then a stage here, and then our final stage. And so if there's no gate, we're assuming that it skips that stage. That's kind of the way this game's played. So let's calculate our first stage of gates here. So it looks like we've got a 0 ended with a 1. So that means we change this to a 0. Let's actually do it. Cross it out and change it to a 0. This 0 changes to a 1. And this just stays as a 1, right? So it changes or stays as a 1. Now, since there's no gate out of this AND here, what happens is this 0 propagates to this OR gate, right? So we got a 0 there. And now we can calculate this stage, right? Let's calculate the rest of this stage. We've got 2 1s, right? We've got 2 1s here in an AND gate, so that means this 0 changes to a 1. Now we got to consider the order of things that happen. This 0 got here before this 0 changed to a 1. So what that means is this 1 changes to a 0, and then after this gate changes to a 1, it changes back to a 1. So this whole time the output should have been a 1, but since we've got these inverters here which take some time to change, we can actually have this small phenomena where it should stay as a 1, but it temporarily goes down as a 0. And luckily, these are actually pretty easy to fix, right? We just had to find our edges and create implicants that connect them. So we kind of already identified that this is where our static hazard was, and so if we create an implicant that connects them, that's this implicant here. And so that means what we need to do is OR that with B is a constant, so we've got B, C naught. So what we would do to our circuit here is we would add, well, we're going to need an inverter for C, so we'll add an inverter for C, and then we're going to need to bring in B. So let's add another AND gate here, and no, it's going to get a little loopy. Let's just say that we've got B, right? So we know that these are connected. And of course we're going to have C as well. And this is going to go into our OR gate as well. So now when we're in this state, when we're in our red state, that means we've got a 1 here and a 0, or sorry, we've got a 1 there, right, because it's going through an inverter. So that means our output is also a 1. And so what that really means is we've got 2 1s coming to this OR gate, which is still a 1. And as we change from this state to this state, it doesn't matter any of this timing mumbo jumbo that's happening. This guy we're still going to be in this implicant, so this is still going to be outputting a 1, and so that's going to make it so our output stays as a constant 1. So that's kind of the idea, what we're doing in what I want to say, not in practice, but this is what we're doing in reality when we're adding implicants here, is we're adding more gates that will keep it locked in a 1 even as it transitions from one state to the other state. Because when you transition from state to state, that's when the static errors can happen.